And this worksheet's on variation parameters. At 1:35, we'll start with physics. So, for the most part, we have moving through these. Just going to highlight some important concepts. Hooke's law. You stretch or compress a spring, it exerts a restoring force that is proportional to the amount of this stretch or compressed in the opposite direction. Newton's second law of motion. Sum of forces is mass times acceleration. The equation 16.5 describes what's known as simple harmonic motion, free undamped motion for the spring. That's when there is no resistance. You got the period of the motion. And you have frequency, which is 1 over the period. Omega is your circular frequency. And omega is given from that equation. X double dot plus omega squared x equals 0. So it's the coefficient of x. The square root of the coefficient of x. Then you have free damped motion. That is when there is resistance. Right? So unlike simple harmonic where put the spring in motion, it's just going to keep going. Probably the easiest way to think of that is a pendulum. Imagine a pendulum just keeps swinging with no resistance. It won't stop right, just keep in that motion, the same motion. Damped motion, there is resistance. You swing a pendulum, what happens? It doesn't swing forever, right? It starts to slow down. Unless you have an exerting force to keep it in its motion. For simplicity, we will just assume, like with air resistance, that it's going to be proportional to velocity. Right, then you'll have damping, You have a damping constant, which is your constant of proportionality. They use beta. Right? The equation is called free damped motion. And then you have a damping factor, and you also have a steady state solution, which is what happens when t goes to infinity. Right, 3 cases, I believe there are. We have the overdamped case, a critically damped case, and an underdamped case. Yeah, just read through it. And then if there's driven motion, right? So not only are you now going to put it in motion and assume resistance, but you're now exerting a force onto it as well. Notice that that is going to now be non-homogeneous linear, whereas the other 2 cases were homogeneous. That's where we're going to have a steady state, which again is let t go to infinity. Oh yeah, series circuits. I is the current, LRC, let's see if I remember this, inductance, resistance, capacitance. And I is current, oh yeah, Kirchhoff's second law, and Q is charge, and current is just rate of change of charge. And so L would be your inductance, R is your resistance, C is your capacitance, and E is the voltage. Generally speaking, it's the voltage of the battery. And it goes into your three scenarios of overdamped, critically damped, underdamped. Two kilogram mass suspended from a spring, and we know the spring constant already. 10 Newton per meter. Well, I shouldn't say per meter. Right? Newton over meter, or Newton meter inverse. And it's allowed to come to rest. So we attach the two kilogram mass to the spring. It's obviously going to extend the spring to a new equilibrium position. That's when it comes to rest. That's its new equilibrium length. Then we set it in motion by giving it an initial velocity of 150 centimeters per second. We want to find an expression for the motion of the mass, assuming no resistance of any kind. We will then determine circular frequency, natural frequency, and period for the simple harmonic motion. Yes, this equation was already derived, but I'll rederive it. Starting from Newton's second law, sum of forces is equal to ma, mass times acceleration. And by the way, Newton's wrong. That is not actually true. Sum of forces is change in momentum with respect to time. If you assume constant mass, then yes, that is m times a. Einstein says mass is not constant. Mass is a function of speed, and speed is a function of time. We're going to ignore relativity for now. Because that would just make things way more hideous. Well, acceleration, second derivative of position. So it'll be mx double dot equals the sum of our forces. We only have one force. The restoring force. Spring constant times x, but it's in the opposite direction of motion. Mx double dot equals negative kx. They tell us the mass is 2, and we already know the spring constant. Initial position, it's equilibrium, so 0. Initial velocity, 150 centimeters per second. We may have to adjust that though. We are going to have to adjust it because the spring constant was given in what? Inverse meters. So we're either going to have to adjust the spring constant to be inverse centimeters or adjust the speed to be meters per second. And meters per second is going to be easier. 150 centimeters per second is how many meters per second? 1.5. There's your initial value problem. That's what we're now going to solve. I'm going to first rewrite just put it in standard form. All right, so 2x double dot plus 10x equals 0 with the same initial conditions. Notice that is all the models that we look at are second order. We're not modeling anything above second order. That is homogeneous, linear with constant coefficients. Oh, we know how to find that solution, right? What do we have to do first? You don't actually have to know. You can, it'll just get you the same result. So when you want to solve an homogeneous equation, what do you have to do? Set up the what?
Integrating.
The what?
Integrating.
How do you find the complementary function? Which, by the way, there is none in this case because it is homogeneous, but it's the same setup.
The auxiliary?
You need the auxiliary equation. What's the auxiliary equation here?
2x squared plus 10.
What was it?
2x squared plus
I would not use x. R, M. I wouldn't use x because x is our dependent variable here. Solve that. What do you get? R squared is negative 5, right? So what's R?
plus or minus root 5i.
What is your solution? Now remember, you have three cases when you solve the auxiliary. Distinct, repeated, and complex. So what we can say?
C1 cosine root 5 plus C2 sine root 5.
Close.
Root 5t.
Root 5t. That's the equation of motion, the family of solutions, right? We now apply the initial conditions, which means we need to take the derivative of that. What is its derivative?
Root 5t.
Close.
Or then plus. No, just the first time.
There's going to be a plus, but for that first term, that's not
I
correct.
just didn't bring out the root 5.
You didn't do chain law.
I didn't bring up root 5. Negative root 5. Simple sine.
X of 0 is what? I don't want the initial condition, just given that function. What is x evaluated at 0? You have C1 cosine 0, right, which is what?
C1.
And then plus C2 sine of 0, which is what? And that had to equal 0. C1 0. Here's a nice little trick. It's not going to matter here, but you already know C1 is 0, so you can ignore the C1 term. Doesn't matter because sine of 0 is 0, so it's going to cancel it out anyway. That's going to be what? Root 5 C2? And what does that have to equal? 1.5. Y2 now. C2 is 1.5 over root 5, or 3 over 2 root 5. Again, or if you want to rationalize it, 3 root 5 over 10. Notice I'm making a major assumption here.
With the roots positive.
I know that the initial velocity was exactly 150 centimeters per second. So I'm saying that's 150 point an infinite number of zeros. And I'm not rounding it. Otherwise, I'd have to actually use sig figs with 1.5 over root 5. So I'm just going to assume that that is an exact measurement. And there's no error whatsoever. And there is your simple harmonic motion. But we're not done. So we wanted the circular frequency, the natural frequency, and the period. We call circular frequency omega. Remember, that is given as omega squared is k over m. K is the spring constant, m is the mass. Spring constant was 10 Newton inverse meters. Mass was 2 kilograms. So we're going to have omega squared being 5, and what is that? Inverse, so the Newton inverse meters, inverse kilograms. Omega is root 5 hertz. We always take the positive group. Right? A negative frequency doesn't make any sense. The natural frequency is defined as f, and it's just your circular frequency divided by pi. Root 5 divided by 2 pi hertz. Finally, your period, capital T, always just 1 over the frequency. And periods measured in seconds, in this case. Ten kilogram mass attached to a spring, stretches it 0.7 meters from natural length. Mass is started in motion from the equilibrium position with an initial velocity of 1 meter per second in the upwards direction. Find subsequent motion if resistance is negative 90 x dot. again, we start from Newton's second law. Sum of forces, mass times acceleration. That's Hooke's law. So that's your restoring force, negative kx. We also have air resistance. We have resistance. That is negative 90x dot. That is your sum of all the forces. That has to equal mx double dot. We know the mass. We do not know k. The restoring force, though, notice these are magnitudes, is equal to the weight, but in the opposite direction. Yeah, the magnitude of restoring force is equal to the weight. And so it's going to be in the opposite direction of force due to gravity. S is length. I should say it's the distance from natural length. Positive if you're stretching, negative if you're compressing. Force due to gravity. That's weight, which is 10 kilograms times g. The acceleration due to gravity. We're going to use the approximation 9.8 for simplicity only. If this was physics, I'd be sticking with G. Actually, if this was physics, I wouldn't be doing this problem. That's a different story. How much was it stretched? Zero 0.7. Isn't that 10 to the 7, 10 to the minus 1? So can I say that's actually 100 over 7 times 9.8? What's 100 times 9.8? $980. What's 980 divided by 7? $140. And that should be Newton inverse meter. There's your spring constant. So that is the model of motion. That's applied to initial conditions. X of 0, what was its starting point when motion started? Equilibrium, which is 0. What was its starting velocity?
meter per second.
In which direction? Up, so positive. Now we can solve. What does it want? It wants essentially a function for position. There's your auxiliary, right? Which we can simplify. You should get -7 and -2 as your roots. What's your position function then?
C1 is -17 plus C2 equal to -2. I think it should be negative. Because the storm force was negative, right? And that's the upwards direction. That would be compressing it, which is the negative direction here. Velocity should actually be negative. Technically, it doesn't change anything up to this point. Let's also take its derivative. What's its derivative? So C1 e to the -2 plus -2 C2 e to the -2.
Evaluate both at 0. Solve that system.
equals negative C2.
So what? 7, 5C1 has to be 1, which makes C1 1/5.
Negative.
Right, so 7C1 plus 2C2 has to equal positive 1, right? If you plug in C1 as negative C2, that would give you what, 7C1 minus 2C1? 5C1 has to be positive 1, which makes C1 positive 1/5.
Oh,
I rewrote in my head X dot as all positives.
Yeah.
I just multiply through by a negative. Doesn't matter, you should get the same thing regardless, right?
Yeah.
If you don't, you should get negative 5C1 equals negative 1.
It's negative 7 times
Negative 2.
C2.
Yeah, negative,
which is
negative.
Positive 7.
Yeah, you get negative.
C2.
Oh, you're solving for C2. I'm solving for C1.
Oh, I was.
C2 would be negative 1/5. I solve for C1 first. And C1 positive 1/5, C2 negative 1/5.
Same to you. At least should be.
So X of T (1/5) e to the negative 17 minus e to the negative 2t. Right, that describes the position of the mass at time t. And just to verify, if you take that limit as t goes to infinity, what do you get? 0, which is what it should be. All right, your oscillations slow down eventually back to equilibrium. This one, I believe, has a what happens to that E? I think this one has a driving force as well. In fact, it's the same spring as the last problem, except there's now a driving force of 5 sine t. Okay, so again, you want the position, and then find steady state solution. I'm just going to keep that in the back of my mind. I'm still going to drive. Sum of forces, MA. In this case, sum of forces negative 140x, right, that's the restoring force, minus the 90x dot, the resistance, plus our driving force, 5 sine of t. That has to equal 10x double dot. Mass times acceleration. We already know the complementary. Right, we did that already, no need to redo it. Now I have to find the particular. How do you want to find the particular?
Variation. Parameters.
You want to use variation parameters? You can, you're not wrong. Yeah, it's called undetermined coefficients, which means you need a form for the particular solution first. You can use variation parameters. What you're going to have to do first, though, is divide everything by 10. So your G would be 1/2 sine t, not 5 sine t. Your y1 and y2 should still be the same. Right? Dividing through by 10 doesn't change your complementary. I'm going to use undetermined coefficient because it's easier to do. It's easier to do by hand. Then we're going to need to plug those into the original. They're going to save you the headache, the algebra. When you do that, we should get 130a plus 90b times cosine plus negative 90a plus 130b sine. That has to equal 5 sine of t. Coefficient comparison. that. Verify that. When you solve that system, you get A to be negative 9 over 500 and B to get 13 over 500. Oh, apparently I'm Christina now. That's nice. I love those scam texts. Also, apparently have multiple homes in several different states. Also, apparently applied for some job in Texas at one point. I got a call saying they wanted to interview me. I don't even remember writing that application. Is that what you got? Yeah. Perfect. That is our position of the mass with respect to time. Now we need to solve for those C1 and C2, right? Which means we're going to need x dot. Thank you for that. X of 0. What's cosine of 0, 1? Sine of 0 is 0. And that has to equal 0, right? X dot of 0. That has to be negative 1. Wait a minute, hold on. I need to make a slight change. I mixed up my A and my B. A was attached to cosine, not sine. Is That's gonna change. Next dot. Cosine, that's plus sign. That's gonna change this to what, minus 9/500? That's gonna change this one to what, plus 13/500? I think that's right now. Does that match what I have? Yes, that now matches what I have. What do you get for C1 and C2 when you solve that system? Just verify, because I'm going off of what I noticed last time. My notes, I did positive one instead of negative one, and it just flipped the signs. So if that pattern holds true, that should be the solution. C1 and C2, just verify that. Way too easy to get on myself. Is anyone verified it yet?
No. So that's a zero.
Well, no, those systems are correct. I'm talking about the solution to the system, C1, C2.
Yeah, that's what
C1's 101/500.
one can actually plug them both into that's a zero.
Oh, I see what you're saying. You're just verifying.
Is that not what you?
I was expecting to use the solve feature. What'd you get?
99/500 and -9/50.
So 99 and -9.
Yeah.
Confirm. That sounds familiar. Oh, just checking. That sounds familiar. That's right. My notes were wrong.
I guess it looks like.
No, it could have satisfied x of 0, but not x dot. Remember, it has to satisfy both simultaneously. So that solution could have satisfied x of 0, but it wouldn't have satisfied x dot of 0.
Yeah, when I did x of 0, I got like -0.00, and then straight from this.
Oh, which means it didn't satisfy x of 0.
Even though it was like super.
Doesn't matter, it wasn't exactly 0.
Well, then I was just wrong. Not the first time. For sure.
It's good. You learn from mistakes. Just make sure your mistakes don't kill anyone, Mr. Engineer. Motion then.
I'm not a Soviet engineer. I don't build bridges.
It's this, right? For the steady state, take a look at this limit. What does this do as t goes to infinity? Goes to 0, doesn't it? What does this do as t goes to infinity? Goes to 0? What is this doing? What is this doing? So isn't that limit the same as that limit? So that's your steady state solution. Which notice was our particular solution here. Right, so what does the steady state solution mean? Well, it just means given enough time, that's going to be the motion. That's going to be the position of your mass.
So what's the difference between the particular and steady state?
In this case, there was none.
Definition.
Particular solution is the solution due to the driving force. Due to the nature of the complementary, though, since that went to 0, that is your steady state. But that may not always be the case.
And then steady state is just when
Because what is the mode, essentially, what is the motion
as it
stabilizing out to?
Gotcha.
What's it steadying out to? That's why we call it steady state.
Gotcha. So like giving it an amount of time.
You know, what's it eventually going to do? How's it behaving? What's it going towards? Right, in this case, because of the driving force of 5 sine t, the spring is essentially going to settle into a sinusoidal motion. which is simple harmonic, right? So it's heading towards a simple harmonic. I hate circuit analysis. So I'm not going to rederive Kirchhoff from Kirchhoff's second law, so I'm just going to use what I already derived. Right, by the way, in an actual physics course, all these introductory slides, that would have actually been a physics problem. That derivation. And then I would have moved on with my life. I'd let you engineers plug in the numbers. I'm a theoretical physicist. What is the inductance? In this case, it's 20. I'm trying to remember. I think inductance, the unit is henries. If I remember my E&M correctly. What's this one asking for? It's asking for charge, right? Yeah, it's asking for charge. So it's 20 Q double dot plus the resistance Q dot. Okay. Resistance, the unit is the ohm, plus 1 over the capacitance Q is equal to the applied voltage. And again, if I'm remembering my E&M correctly, I think the unit for capacitance is the farad. Short for the Faraday, I think it is. And obviously voltage is the volt. What are we told? There's no initial charge but there is an initial current of 1 amp, 1 ampere. But current is change in charge. There is the model. We want to find Q of t. By the way, if you divide that by 2, just replace X with Q. Oh, that's nice. The solution should be almost identical. Just wanted to verify it. I was looking at the wrong thing. Solution is almost identical. There has to be one slight change. X dot was -1 here. It's +1 for our problem. Those signs just flip. That's going to be the solution. So I'm going to be clever. I'm going to say and then similar argument from 3. There's your charge. Oh, that was nice. Just like that. I'm going to have to redo any of the work because I already did it. This one's interesting. So we have an RCL circuit again. Assume no initial charge, no initial current. We want to find the current of the system, not the charge of the system. Kirchhoff's second law would give us 12, right? But this gives us for charge, right? So remember, I is Q dot. So this would be Q double dot, Q dot, and Q. That's not what we want. We want I. We want current. Differentiate that. This gives us I of 0, 0. But we have a problem. We need I dot of 0. I'm out of time, so I'll just explain. Solve this for I dot, evaluate it at 0. Because you know Q of 0, you know I of 0. That will give you this. I dot of 0 is 24. That's your system that you have, or that's your equation that you have to solve for current. I'll leave that for you to do. I'm assuming my notes are correct. That's what I thought. Looks like this was actually pretty simple to solve. So I'm assuming my arithmetic here is correct. But just solve it on your own. I did the hard stuff. I did the hard part for you and set it up. And so that's your physics lesson. Again, basic physics. This was like real basic mechanics and I'll just show this. Second group assignments due the 10th. Continue working on your reference sheets. Third quiz will be available today after class. We do next Tuesday. As a reminder, we are not meeting next Tuesday. However, if you have other Tuesday classes, they probably are meeting. School's not closed on Tuesday. I'm just taking the day off. And I get a physics worksheet, which is always fun, right? We all love physics.
Our previous worksheet, we finished, you just skipped one. I tried that one. It's gonna be long. Pretty sure which one we got.
My job is taking math classes over the summer.
Yeah.